Okay, this part of the lecture is going to cover some concepts that relate to the preparation of conjugated dienes and some of their reactions. And we're going to start by reviewing just a little of the reactions that we already know from alkenes. And so when we talk about alkenes, we talked about how to make the double bond by using the reaction we call dehydrohalogenation. And if we want to make two alkenes, then we could use double dehydrohalogenation. And so we'll review that a little bit. And we'll also review allylic bromination from chapter 10 and talk about why when we do double dehydrohalogenation it's going to favor going into conjugation instead of making a triple bond, which goes back to chapter 9. It was kind of alluded to at that point. We'll also talk about dehydration. Again, that's a review, and using that as a double dehydration, we're going to have some new conditions. So out of all of this, all of it is stuff we've already had, except for the very last conditions that we're going to use for double dehydration. So in chapter 8, we learned that we could make alkenes by removing the elements of the HX, and that's called dehydrohalogenation. And you could do that by heating up a molecule that has a halogen and an adjacent hydrogen, and using a base. Heating it up facilitates the elimination reaction to make the alkene. And I haven't drawn in the side products here. Well, here's an actual molecule. Now in this case, if you look, the carbon that has the halogen on it, on the adjacent carbon you have a hydrogen here or hydrogen here, so you could conceivably make either one of these two products. And in the context of chapter 8, we talked about the fact that we tend to see as the major product the more substituted alkene. This alkene has 3 carbons attached to it. This one has only one other carbon directly attached to it. So this one is a tri-substituted double bond. This one is a mono-substituted double bond. The more substituted it is, more favorable. It's more stable. Energetics favor the preparation of that. Now, we looked further in chapter 11 about the mechanism of this reaction, which could be either E2 or E1. And when we learned about that, we learned that sometimes this business of making the more substituted alkene, it doesn't necessarily always happen if the reaction is going through an E2 elimination. It will always happen that way if it's an E1. Now, it turns out this reaction is actually E2, but either one of these positions can get the right geometry, which is the anti-periplanar geometry, for the E2 elimination. So this is the right answer in any respect. Whether you worry about the mechanism or not, it is going to work out to be the major product is the more substituted, or what we call Zaitsev's product. So here's an example in chapter 11 where you had to have the anti-periplanar geometry for E2. So if you look at this on a ring, the hydrogen has to be anti-periplanar, which means approximately in the same plane but on the opposite side. Well, this hydrogen is in the right position to get that geometry for this elimination to be E2, but over here the position is occupied not by a hydrogen but by a methyl. If this guy undergoes elimination strictly by E2, the only place it can put the double bond is right here, which is why this would be the only product which is observed. So that's not the Zaitsev product. The Zaitsev product, or the more substituted alkene, would have been to put the double bond here, which turns out to be right here. But you don't get that if this is an E2 elimination. We're not going to spend a whole lot of time talking about those kind of details in the context of this semester, but they do sometimes come up, and it's important to kind of keep those in the back of your mind. Now, if you take this further and you want to make 2 double bonds, which is what this chapter is about, molecules that have multiple double bonds, then we need a second a second halogen in there to come out and make two double bonds. So where could you get that? Well, if you had an alkene, you can turn that into two halogens, which is halogen molecules. So I have an example here. And then you could take out both HX across here, or HBr across here, and then another HBr across here, and you can get this molecule. Sometimes it takes a little stronger base to get that to work. Or alternatively, in chapter 10, we talked about doing allylic bromination, and we use NBS for that, N-bromosuccinimide, and that's actually a free radical reaction. And in cyclic cases, simple cyclic cases, you only get one product, so that's fine. That's a useful thing. And then you do the elimination on that, and so you get the same product. I alluded to this earlier. You could conceivably take a hydrogen from here to take out an HBr here, and then a hydrogen from here and take out an HBr here, and you can get the triple bond there. But that's not favorable for one reason, because you're trying to put a triple bond in the ring, but also this conjugated system is more stable than the triple bond, even if it weren't in a ring. And you're also not going to observe this kind of thing, which is called an allene. Again, in a ring, that would be very easy to form because this carbon's sp. But more importantly, the conjugated system is also more stable even if it weren't in a ring. So you won't see any of that kind of thing. All right, what else? In chapter 8, we also talked about the dehydration of alcohols to create the double bond. And again, we talked about favoring the more substituted double bond. And that reaction actually is an E1 elimination. So in chapter 11, we talked about that. If we're using sulfuric acid and heat, it's going to go E1 and favor the more substituted alkene. In chapter 17, we added another reaction that's a dehydration, which actually tends to go E2. So those were things that we've seen already. So this was the early reaction to take an alcohol and heat it up with sulfuric acid. So again, you're looking for the adjacent carbon hydrogens, so you can take out and put the double bond out here or here. Well, the more substituted double bond here is going to be favored because that's a disubstituted double bond. That's going to be favored over the monosubstituted double bond following this E1 elimination. And if you go into chapter 17 and look at this this phosphorus oxychloride, POCl3, that one actually goes by A2, but again, there's bond rotations here, so either one of these can form the anti-periplanar geometry is available, so it's still going to follow Zaitsev's rule, and you'd have the same product distribution even if you use that. So, if we want to do double dehydration, we again need two OHs in the same molecule. We did learn some ways to do that, and one example is we could start with an alkene and use the osmium tetroxide, and we could get a cis diol. And so rather than heating it up with sulfuric acid or the other, the POCl3, what is preferred for doing the double dehydration is aluminum oxide and heat. And the reason this is preferred is this is like a powder. It's a real fine powder, kind of like baby powder, and industrially this is put into a column, and they force hot carrier gas up through it, and then they bring in the diol, and it causes a dehydration, and so your other product is water, and the water separates from the diene, and it doesn't consume the catalyst, and this forced air up through this bed actually creates what's called a fluidized bed. When you see this powder is so fine, you know, if you have a bottle of baby powder and you squeeze it real quickly, you get a puff of air out the air and the powder out the top. Well, if you could contain it and look at it with air bubbling through it, you'd see it actually bubbles kind of like a liquid. So that's why it's called a fluidized bed. So that's a pretty cool industrial route. And in a laboratory situation, you can even make your own fluidized bed, although it's a little easier industrially, more common industrially. But that's the only new preparation of dienes that we have in this chapter. Everything else is review. So before we start talking about the reactions of the dienes, I want to just give you a little refresher on alkenes, which I'm going to call monoenes to be parallel with dienes. So this is back in chapter 7 and 8. We talked about alkenes, and we started off, pretty early in learning about reactions. The electrophilic addition of molecules of HX, so hydrohalogenation. And we talked about Markovnikov's rule and the way this reaction goes. So the pi cloud of the electrons reacts with the electrophilic end, the positive character hydrogen of this HX molecule, and then that causes the halogen to go ahead and take this pair of electrons and gives you a carbocation, which is on the more substituted carbon. And then even though the halogen is pretty happy to be an anion, the carbocation attracts this halogen back. And so we always know which carbon is going to get the hydrogen. It's going to be the less substituted carbon, because that electrophile is going to go on first and give you the more stable carbocation on the more substituted carbon, and then the halogen, which is in the second step, is called the nucleophile. It will go on to that. And this carbocation here that I've represented, if we assume that R is just more carbon, then I have two different degrees of carbon here, and that's when I can tell, which carbon is going to get the hydrogen and which carbon is going to get the halogen. If they were the same degree, then I would get a mixture. And in this case, when this chunk of carbon is just, more plain old vanilla carbon, then this is a secondary, in this drawing, this is a secondary alkyl carbocation. Here's an example. So I have a simple alkene and I react it with HCl. Here's my carbocation, and then the chlorine goes on to the tertiary carbon. Now, if you have a non-conjugated alkene, it can be a diene, but this one is going to act separately from that one. This molecule, they didn't balance the equation, but if you had put in 2 molecules of HCl, then you would get Markovnikov addition on both ends, and everything looks just fine. And so I added this note here that we're assuming that we have excess HCl. I know organic chemists tend to be pretty sloppy about balancing our equations. But now let's see what happens if this time we're going to assume we only have a one-to-one relationship of HBr and a conjugated diene. And then we get this result. So we get some of this product right here, which looks, pretty much like you would expect if you just thought about this as an isolated double bond. You do the Markovnikov addition, and you get the hydrogen on the less substituted carbon and the bromine on the other carbon. Everything is all good until you look down here and you say 29% of this stuff is something else. You got the hydrogen at this end and the bromine at the other end, and how the heck did that happen? Something is going on here that's not like your plain old vanilla double bonds. And they've added some notes here. They call this 1,2 addition because the hydrogen and the bromine went on to adjacent carbons. The 1,2 in this particular example could refer to the carbon chain numbers, but that's not really what they mean. It means adjacent carbons, as opposed to 1,4, where they're 4 atoms apart. The hydrogen and the bromine are 4 atoms apart on this chain. And again, like I said, it could refer to the carbon numbers, but it really doesn't have to. So we want to know, why are there 2 products, and how did we get this bromine on the other end, and more importantly, how did the double bond get in the middle? That's not where it was initially. And also, you notice that we have a product mixture, and we're interested in, is there any way to manage that mixture? Is it just a hopeless kind of situation? So in order to understand that, we need to think about the mechanism. And so if you think about it working just like a plain old isolated double bond, and go back to what we were talking about earlier, the pi system reacts with the electrophilic end of the HBr, the hydrogen with the positive character, spits out the bromine anion, and you get this carbocation. But look at this carbocation. Not only is it the more substituted carbon, but it's also right next to this pi system, and we call that an allylic position. And so when you have an allylic carbocation, we talked about that in chapter 10, you can do resonance. So these three atoms are sharing these two electrons, and here's kind of the other picture. Remember, the idea of resonance says that it's not really this picture or that picture. It's really a conglomerate of where these three atoms are sharing these two electrons, and there's positive character at either end. The carbon in the middle is always happy. But we've got positive character. If you looked at it in the electrostatic pictures, I think blue is kind of positive and red is kind of negative. Well, these two carbons would have some blue character to them, but the carbon in the middle would always be okay, so it would have a lot of red there. And so we need to be able to recognize that we have this resonance structure stabilizing this carbocation intermediate. So it's a secondary. It looks like secondary alkyl here, but it's really not. It's secondary and it's allylic. In this structure over here, it's primary and allylic. So there's a little bit of difference between those two guys, which we'll also talk about. So how you get to the product is then the bromine either reacts here, and so you get the 1,2 product, or it reacts when the carbocation character here, you can get the 1,4 product. And remember, it's really one structure, and so it's just which end of that positive character does the bromine happen to hit. And that still doesn't necessarily tell us, are we always going to get this mess, this mixture of products, or can we control it at all? And so we need to look at those two structures, and we need to think about how these things form. And I've kind of hinted at this a little bit. The degrees of the carbocation character in the resonance structure are not the same, nor is the character of the double bond the same. So let's go back and look. This one is a monosubstituted double bond with a secondary carbocation. This one is a disubstituted double bond with a primary carbocation. So there's and maybe you need to decide, or we need to know, what's more important in the stability argument, the carbocation or the double bond. And so it turns out that if you think about it, the first one to form was the, let's go back again. This is the first carbocation that forms. When you first start this reaction, you get this guy. So the hydrogen goes to the less substituted carbon, and because of symmetry, we can't tell the difference between the two ends. So a hydrogen goes onto an end, and then you get this carbocation. And so that happens first. So that's the first formed carbocation. And some amount of time, it might be an infinitesimally small amount of time, but some amount of time has to pass before resonance really establishes that there's, this real smear of these two carbocations. And so when it starts resonating, it goes between the secondary carbocation and it's got the less substituted double bond. But when it resonates, you've got primary carbocation character, which is less stable, but the double bond is more stable. And again, time is a factor for the resonance to occur. And there's also a difference in the stability of the two products. So if we look at the two products that ultimately come out of this is a monosubstituted double bond, and this is a disubstituted double bond. So if all we were worried about was the double bond, this would be the more stable product. And the terminology, remember, this is the 1,2 product and this is the 1,4 product. And so So let's see if we can kind of make some sense out of all of this. We've got to have some information here. All right, so we're going to summarize. The 1,2 product is a monosubstituted alkene. The 1,4 product is a disubstituted alkene. There's a difference in stability because of the substitution patterns, and so that means the enthalpy for these two products is going to be different. Now, how different it is depends on your particular situation. In this particular case, they might not be all that different. I've drawn it as trans, and it could have been cis, and we're not even worrying about that. But if you go back and you review the order of stability of alkenes, the more substituted, the more stable. So these two are kind of next door in terms of stability, but if I was going and comparing a monosubstituted to a trisubstituted or a tetrasubstituted, there would be a bigger difference in enthalpy. So what else do we know? Well, let's see. The 1,2 product forms first. It can form immediately. As soon as you form that first carbocation, the bromine hits it immediately, then you get the 1,2 product. But the 1,2 product is less stable. And so when you have that situation, a very quick process, we call that the kinetic product. And so what's controlling the kinetic product is a fast and irreversible set of conditions. And I'll come back to the idea of what I mean when I say it's irreversible in a minute. If you're going to observe the 1,4 product at all, you have to have had some little amount of time, and it has to have gone through resonance, and if you get it, it will be more stable. And so you can favor how much of that you get by allowing equilibrium to occur. And equilibrium means that you've not only got more time, but usually you have a little more energy in your system. And the energies of the study of the energies of the products is thermodynamics. And so if we're allowing for equilibrium to occur and worrying about the energy, the enthalpy of our products, that's a thermodynamic argument. And so we're going to call the 1,4 product the thermodynamic product. And so ultimately what we want to know is, can this help us manage this reaction? And the answer is yes. So we have if we have fast and irreversible conditions, that means not very much time, so 10 minutes, 20 minutes, something like that. Not very much energy, so low temperatures like 0 degrees or 510, something less than room temperature. That would be what we would consider to be fast and irreversible conditions. If you have a little more time, like an hour, 2 hours, definitely more than an hour of time, and a little more energy, so things that are warmed up definitely more than room temperature, then you could establish an equilibrium situation, and that would favor the thermodynamic product. It might help if we draw a picture. And by the way, I'll tell you, I really don't like the pictures in the book because some of the pictures aren't complete. And if you rely strictly on the pictures in the book, you kind of miss some things. So really use my pictures to help you understand this. I've added to the pictures in the book. So you're starting from 1,3-butadiene in this example. It is going to start the reaction with, in this case we're using HBr. So it starts reacting with the HBr, and what you have at the top of this hill, the first transition state, is the hydrogen is starting to get bonded onto the molecule and starting to create the carbocation, which is what you get when you get down here to this reaction intermediate. So you've gone over this hill, you've got this carbocation intermediate, which is resonance stabilized. Okay, so I've added the resonance stabilized carbocation intermediate here. Now, if this guy right here reacts, if this end of the resonance structure reacts, you get the 1,2 product. If it goes through resonance and this end reacts, you get the 1,4 product. Now, one thing you might ask is, why do we have a difference in these barriers? And it's because there's that little bit of extra time and energy to cause the resonance structure. So even when we've drawn them right here together, there's just this little extra bit of time. And you notice that if you kind of extended this out, that the pink one has crossed the black one. And so the 1,4 product is more stable than the 1,2 product, and so you see a small difference in the energy. And I've added in here the overall energy of the reaction to go to the thermodynamic product, which I abbreviated with a T here, so that's the 1,4 product, is you get a more enthalpy out of that reaction than for the kinetic product, which I put the K there. Okay, so the difference is this difference in where they are in the graph. And I told you how different in energy these guys are will depend on the particular example. So what are we going to do? How are we going to manage this? So let's do what I call panning for gold. We're going to imagine that we start this reaction, and we assume that the kinetic product is going to form first, because that's what you get, when it first comes out and hits right away. And if there's enough energy to get the whole thing going, then, you're going to get that first 1,2 product. And, but the only way that you can get any of the other product is if it gets to going through resonance. And you can facilitate going through resonance if you add a little more energy to the system. And again, it may help to look at the picture again. So what we're saying is, I've added some things to try to help explain this. Okay, so the energy of activation, to go over the first step, is the energy of activation to the first transition state. Okay, so this is the first transition state. The energy of activation for the second transition state depends on whether you're talking about this one or that one. So I've got two energies of activation for the second steps. Okay? But if everything went to this kinetic product, the 1,2 product, then, you wouldn't see any of these other guys except if resonance occurs. But if you wanted to reverse, reversing means the energy of activation to go back to the intermediate. Okay, so it comes back apart again. If this reaction is reversible, the energy of activation to reverse the kinetic product is this much. Now, if you look at that, okay, this energy of activation compared to that energy of activation are pretty similar. Okay? So what happens if you heat the fool out of this thing? Well, everybody's reversed and you have no control whatsoever. Okay? So what you need is a little finesse. You need to supply enough energy of activation for this guy to be reversible, but not this guy. Now, I didn't draw this one in, but you see the difference from the top of this hill to the bottom of this hill is going to be more than either of these other two energies of activation. So you want to have enough energy, and remember I said you just need to warm it up a little bit more, maybe 60, 75 degrees, something like that, so that some of this that forms can go back to here, and then it's got an opportunity to go over this hill. So you can set up reversible conditions or equilibrium conditions, excuse me, to get this product. I know this is kind of a hard concept, and sometimes we do a lab, which really, really helps, but sometimes we don't. So I really don't know whether you'll see something like this in lab, but there really is a noticeable difference in what you get depending on the reaction condition. If it's fast and cold, you get a lot of the quick and dirty product. If more time and energy is supplied, then you can get a lot more of this product. Now let's go back and consider the reaction that we started out looking at in the beginning. So we're talking about if the reaction has an opportunity to achieve equilibrium, slosh back and forth, and you don't have so much energy in the system that you swamp your finesse, then you can get a fair amount of the thermodynamic product to form. If you don't want that, then you just let it run at colder temperatures for a short amount of time. So we have a situation where you have two possible outcomes in competition with each other. If they have different amounts of energy, then by choosing the right condition, we can favor the production of one over the other. And how good the control is really does depend on how different in energy they are. And, it may be 60-40, it may be as good as 95-5. It really just, is a case by case. So here's the one that we started out with. So we're going to go back and consider, what kind of conditions would they have had to have used because they got mostly 1,2 or kinetic product. Okay, we now know that this is the kinetic product and this is the thermodynamic product. Since they don't tell us the conditions, but we know we got a lot of this, that gives us the idea that, well, if we were going to guess how they ran this reaction, probably was a short time, 10-15 minutes, and a fairly low temperature. And that's how you would control it. So here's one other example. Suppose that you take this conjugated diene and you put in one equivalent of chlorine molecules, and I have actually specified conditions here, 2 hours and 65 degrees, which is, a longer amount of time and not too hot, but more energy is available in this system. And we want to know what we'll get. So you need to start out by drawing the carbocation that you're going to get. And since it's symmetrical, it doesn't matter which double bond you start with. One of these double bonds is going to get a chlorine atom, and the other carbon is going to get to be a carbocation. It's always going to go to the one that can be in the allylic position. Okay, the carbocation will go allylic. So the chlorine's out here at the end of the system, and the carbocation is allylic. And when it resonates, remember you flip these two guys, and so now the chlorine that went on first and the carbocation are either 1,2 with respect to each other or 1,4 with respect to each other. Now if the chlorine goes on, the second chlorine atom goes on this one, you're going to get the 1,2 product. If it goes on this one, you're going to get the 1,4 product. And so what else we want to do is we want to label these things. So this one is the 1,2 product, and I said it's the minor product, or the kinetic product is minor because under the warmer conditions at the longer amount of time, that's going to favor the thermodynamic product. And in case you're wondering, okay, this double bond is tri-substituted, this double bond is tetra-substituted. Remember, tetra-substituted double bonds are more stable than tri-substituted double bonds. So this one should be the major product, in enthalpy-wise, would be more stable. You can also assume that the 1,2 product is usually the kinetic product, even if you're not sure about the double bond positioning. If it's more or less stable, just 1,2, just a straight 1,2 is going to be the kinetic product. So for this kind of question, we should be able to take an example diene and some kind of electrophilic conditions and draw the resonance structure just like in the previous example, and draw the structures of the intermediate resonance stabilized cation and products, label them as to kinetic or thermodynamic. You should also be able to draw a reaction energy diagram, and you should be able to figure out which one is the major product given whatever kind of conditions you have. So that is the end of the section of the chapter on conjugate addition.